Alright, we're working with a voltage divider here. We have two different places where we could plug in the load, either between A and B or between B and C. So first, without calculating anything, we want to know whether the voltage delivered to the load would be higher in position 1 or position 2. Well, the current, without a load there, the current is the same throughout the whole circuit. So if I have the same current going through a 3 kilo ohm resistor as I do through a 1 kilo ohm resistor, Ohm's law, delta V equals IR, tells me the I's are the same and the R is bigger, then the delta V will be bigger for the bigger resistance. So position 1. We have the same current as the other position but a bigger resistance. So whatever the resistor that's in parallel with the load is, whatever the voltage is across that, that's the voltage the load will get. The loop rule guarantees that. So we want the open circuit load voltages for position 1 and position 2. We can use our equations, or you could solve the circuit by yourself, either way. So delta V source times R2 over R1 plus R2, and we just sort of switch which one is which. So for position 1, the one that we would call R2, the one that's in parallel with the load, would be 3 kilo ohms. So this is 9 volts times 3 kilo ohms over 3 kilo ohm plus 1 kilo ohm. So it's 3/4 of that total, which is 6.75 volts. For position 2, the resistor switch rolls, so that's 1K over that bottom, which is 4K, so it's 1/4 of that, which is 2.25 volts. Those add up to 9 because plus 9, I have to get minus 9 across those two together. We can't know exactly how much power is going to be used by the voltage divider until we know what the load is going to be, but in this open circuit condition we can get a number, and depending on what resistor we put in, it could be pretty close to that. It's at least the best we can do. So if I want to know the power used by the voltage divider, I can use I delta V, where I'm looking at the total. Okay, so this is the total without a load, right? The total current, so the current in the circuit times the 9 volts, which is what we'll have to lose across both of those together. All right, I'm gonna be lazy here for a second and not calculate the total current first, right? Find the REQ and then use Ohm's law to find the total current. I'm just going to sub in for that, right? That's what I would do, is I would use the battery voltage over REQ, that would be the total current, and times, so that's I, times delta V, it's also the battery voltage. So I'll use Ohm's law to substitute because I know these two numbers. If this is 9 volts squared, and this is 4,000 ohms. So the power used by the voltage divider, again without a load, it'll be a little bit different with the load. We would just figure out how much power used by each of these resistors and add them up. We'll get 20.3 milliwatts for the divider. And we want to know whether the behavior, the load voltage, will be better with 1 ohm or, I believe it was 100 kilo ohm resistor, load resistor. The performance is always closer to ideal with a higher load because adding a very high resistance branch will not draw much more current. It will keep the equivalent resistance of the circuit really close to what it was before, which means the total current will be pretty close to what it was before, so the voltage drop across the non-load resistor will be about the same, so we'll get about the same load voltage. If I were to put a 1 ohm resistor in here, then almost all the current's going to flow through here instead of the 1 kilo ohm. The resistance equivalent resistance of the circuit is going to be much lower because the equivalent resistance of this set will be less than 1 ohm. So I've gone from 4K total to just over 3K total, which means my current is going to be drastically different. My load voltage is going to be drastically different. So voltage divider is always great for high resistance loads.